Okay, let's try that. You hear me in the back? Cool. Day 8, lecture 29. Announcements. So lab this week will just be a chance for you to work on project 2. I think the volume is quite high. Hold on. That's probably better. But yeah, I would say this is one of the heaviest weeks of the whole semester in terms of assignments, because you have homework and you have a checkpoint for project 2, and they're both pretty long. So definitely go to lab this week and use that time in order to work on project 2. Your academic interns, your GSI will be there to help you out. You can also come to office hours. We've really tried to staff up office hours more than usual, but still, if you wait for the last minute, there might be a crowd. So get started today on this stuff. Project 2 is posted, homework is posted, and they're kind of on different stuff. You know, homework is on what we just learned, and project 2 integrates a lot of what you've learned over the whole hypothesis testing and confidence interval unit of the course. Also, project 2 is new. It's about climate change. I've wanted to have a project about climate change for a long time, but never found time to build one. But the staff got together and helped me out, and we put together one this semester. I hope you learned something from it. And since it's new, we'll be asking for your feedback. And if you find something that looks broken, well, maybe it is, because it's a brand new project. But hopefully we've tested it enough that it really works. Okay. Questions about any of that? Don't leave everything to Thursday or Friday night. Okay, this is actually one of my favorite parts of the whole course, because what we're going to do is go back to a demonstration that we did in lecture 10. But now you know so much about averages and inference and samples and sample variability that we can come at it with a fresh perspective and learn a little bit more about what we were doing. So once upon a time, we tried to make predictions. I'll remind you, don't worry, you don't have to remember. But the idea here was that based on incomplete information, we would take a guess about what might happen in the future. And the example that we did was, if a child was born and you knew the heights of their parent, then could you guess how tall they would be when they were an adult, many, many years later? And you can do this by collecting data. So let's take a bunch of adults existing in the world. We'll call them the child, even though they're an adult, because everybody has parents. And the data collection that happened long ago was to actually go find their parents, measure everybody's height. So now you have triples of information: the mother's height, the father's height, the child's height, even though the child is an adult. And you could use that information, so based on another pair of parents, try to guess how tall their child might be. Okay, to predict an outcome for an individual, which is basically this, like how tall you're going to be when you grow up. That's one way you might want to make predictions. You could find others who are like that individual in ways that you can measure. So if you have a new baby, you can't measure its adult height because it hasn't happened yet. You can measure the heights of its parents. And if you can find other parents with a similar height who already have adult children, those are outcomes that you know. So to predict an outcome of an individual, find others who are like that individual and whose outcomes you know, and use those outcomes as the basis of your prediction. Good general strategy. And we did this, I will remind you. In lecture 10, it went something like this. We found a classic data set of families whose heights had been measured. Recall that the child column here is one row per different person, so per different child. Here they all have the same father and mother. And these are the heights in inches of the father, the mother, and the child when the child was an adult. That's why they're not baby sized. And then there was other information, how many children were in the family, their birth order, sex of the children. But we just focused before on, if you knew the parent's height, could you guess the child's height? And so we did this back when we were just learning about manipulating columns, like lecture 10 was ages ago. We averaged the height of the father, the height of the mother, and we built a really simple table that was the average parent height for each child. So here are 4 children in the same family, all have the same average parent height, but the height in inches of the children varied. And that's what we have. 934 people at their adult height, along with the average of their parents' height. Any questions about this? You remember this a little bit? Okay, cool. So what did we do? We drew a scatter diagram. And then we tried to describe this. And we asked, is there an association? What's an association? An association is just some trend in the data, some relationship between the X value and the Y value for any given point. In this case, we do see an association because in general, when the parent average is high, then the child average is on the higher side. And when the parent average is low, then the child average is on the lower side, though with a huge amount of variability. So you can't like measure the parents and figure out how tall their kids are going to be because most people end up somewhere in the middle. And then for any given height, there's just a massive amount of variability in how tall the children are. That's just how humans work. We took this idea of prediction, which was, let's say there's a new child born. You can measure the heights of the parents, average them, and they come out to some particular number. Let's say like 68. So how do we predict how tall that kid is going to be? Well, we take similar instances. That was our prediction methodology. Find some similar instances, so that means other people whose parents average is about 68 inches tall, so that's 5'8", and use that information to guess how tall this kid is going to be. Instead of looking at exactly 68 inches, we went from 67.5 to 68.5, and I just chose a ½ an inch on either side, totally arbitrarily. There's no like reason to do that, but I did it anyway. So now we have a bunch of instances where we know the outcome. And what is the outcome we're interested in? Well, that's the height of the child. So that's its position on the child axis, the y-axis. And we can kind of ignore everybody else. Just focus on other parents of the same height in order to guess the height of this child when they grow up. Since there's so much variability, there's kids that are 60 inches tall, or 61 inches tall, and there's kids that are 75 inches tall, so like 5'1" to 6'3". It's a pretty big range. How are you going to make a prediction? Well, the first thing I'd say is, if you're going to make a prediction, a good thing to say is, I don't know, somewhere between like 5 foot and 6'3", probably. But if they're like, well, we really want to guess a particular number, then maybe the average is a reasonable thing to do. So we averaged the outcomes of the individuals where we did know the outcome. And here we did. So we found just the folks whose parent average was right about the one that we're interested in, averaged the outcome, the child height, and got an average height of 67.62. which we can draw on our scatter plot as a red dot. So all this code just does the same thing we had before, but with a red dot at the average, which is the average Y value among all these dots for all the dots that are within 67.5 to 68.5. And that's kind of as far as we could get in the early part of the course. We could do something fancy like say, well, we did this logic for 68, but we could have done the same logic for 66 or 64. And so we wrote a function to do that. Given any average height of the parents, find all the children who have a parent average that's similar, and then average the height of the children. We wrote this function before, and we used apply in order to call it on every single different child in the data set. Now, why would we do that for every single child in the data set when we already know their heights? Well, we want to know if we didn't know their height and we had to predict it and we were predicting with the average, what would we have chosen? And so for every single point here, if we didn't know where it was on the y-axis, all we knew where it was on the x-axis, what point would we have chosen? We would have chosen something in the average range for this vertical slice. And so we do that for every single point in the data set, and we get something that looks like a line. So the next week or two, we're going to talk about this line, what it means. You kind of already know what it means. It's something about averaging over y's given a particular x. But now that we know something about sampling, we can say things like, what's our uncertainty around this line, stuff like that. It gets pretty cool pretty fast. But before I do that, let me just see if people have questions about this old example and how we got here. Because I went through it more quickly than I did in lecture 10, but that's because you know more and you've seen it before. Questions? You have mastered lecture 10. I guess we'll work on mastering lecture 29 then. Here's a question. Okay. We're really okay? I just went through tons of code really fast and it's okay? Yeah. Yeah, so if you've heard about linear regression, all of a sudden we have a line here, and we got it in a very different way than what people describe when they say linear regression, and yet it is basically the same line, except this is a wiggly version of it. So we're now going to go through the mechanics of what it means to find the linear regression line and how to interpret it. But we'll end up finding the same line that you already found, except we haven't found really an equation of this line yet. All we've done is we've found a bunch of dots on it. And now we might want to figure out what its slope is, things like that. Okay, cool. Okay, when you have two numerical variables, there may be an association between them. You can call that a positive association if, as one gets larger, the other gets larger. Or a negative association, which means as one gets larger, the other gets smaller. In neither case are you saying that changing one would cause a change in the other. You're just saying in this data set, if we look at values on the higher side for x, then they're on the higher side for y, that's positive association. Or if you look on the higher side for x, that's on the lower side for y, that's negative association. I think that trend is something that's just about kind of drawing only lines or only smooth slopes that go up or go down. Whereas sometimes people say, is there a pattern in the data? And that describes a more general class of things. So trends are one kind of pattern, but there can be other kinds of patterns too. Like something might go up and then go down. Or yeah, on Mondays and Wednesdays and Fridays, it's high. And on Tuesdays and Thursdays and Saturdays, it's low. Something like that. When a pattern is linear, that means you can describe the pattern using just a straight line. And when a pattern is nonlinear, it means you can describe the pattern, but you have to do something other than a line in order to describe it. So you have to use a curve or maybe some kind of cyclic pattern, Monday, Tuesday, Wednesday, Thursday, Friday, etc., in order to describe it. But any kind of pattern is an association. And why are associations interesting? Well, they tell you that you have information about the outcome Y, as long as you know whatever is observable X. So for a positive association, if you can observe the X and it's high, then probably the Y is high too. But before you start kind of drawing lines, it's a really good idea to draw the scatter plot and figure out what kind of pattern is there. If what you see looks like has a line going through it, then finding that line is a totally reasonable thing to do. And then you can think about things in terms of lines. But if the scatter plot that you draw doesn't look like a line at all, it looks like some weird curve, then it doesn't make any sense to draw a line through it. People do it all the time out there in the world, even like accomplished scientists draw lines through things that don't look like a linear association at all, because it's the most convenient thing to do. But it usually isn't the thing that tells you the most about your data. What tells you most about your data is to first visualize it and see what kind of pattern you're trying to describe. If that pattern is linear, then you want to try to draw a line through it. And we're going to learn the mechanics for how to draw a line through something, but I don't want you to go through and draw a line through everything, because if you draw a line through something that doesn't have a linear association, it has some other weird shape, then that line doesn't really mean anything. So why did you go through the trouble of drawing it? So there's the motto for the course, I would say. Visualize first, then. Once you see the pattern you're trying to describe, it makes sense to quantify it by trying to find the slope of the line or something like that. Okay, cool. Question? Let's look at some data. Did you see this before? Hybrid vehicles? I don't think so. So this back in like, I think this data set was made in 2015, was one row for every hybrid, meaning some mixture of electric and gas car that was available on the market for, since people started building hybrid cars. The early ones were the Prius and the Civic, etc. And they recorded when they came out, how much they cost. And these were normalized toward $2003, adjusting for inflation. Measured their acceleration in kilometers per hour per second. So how much oomph it has. And then the reason people bought hybrid cars early on is they went really far per gallon. So measure their miles per gallon. And then there are different classes of cars. Okay. Let's look at what's in the data. In 2007, Lexus released the LS600 HL for $118,000, which was, a lot in 2003. It had a lot of well, not the most acceleration. It had great miles per gallon. Well, actually, not that great miles per gallon, but somehow it was really expensive. So I guess as we look through this, we'll find that there's more going on than just the cars that have the best fuel efficiency are the most expensive. There are kind of other things that factor into the price of a car. Okay. The reason you buy a hybrid is because you get really great miles per gallon. The more you pay, if you want really great miles per gallon, 70 plus, you actually want a cheap one. You want pretty good miles per gallon, 50. Oh, you actually want a cheap one. You want okay miles per gallon, 40. Well, you still want a cheap one. And if you kind of want bad miles per gallon, like 20 to 30, then I guess you can spend a lot more money on your hybrid vehicle. So the reason people buy hybrid vehicles is so that they get great fuel efficiency. And then all of a sudden we see, like, the more you pay, the less fuel efficient it is. What the heck could be going on here? Talk to the person next to you. Describe what's going on in this plot. This requires real world knowledge. You got 1 minute. All right, who can tell me about the association between fuel efficiency and miles per gallon and price of the car and manufacturer suggested retail price? Anyone want to try to explain to me what's going on? Yeah. Okay, so there's some kind of negative association. Is it a line? Doesn't really look like a line. It looks like there's sort of a precipitous drop and then it's pretty flat. So if I were to draw a line through these, the line wouldn't actually go near many of the dots at all. It's not really a good candidate for drawing a line. And why is it the case that there's this negative association? Great. So suggestion is maybe the more expensive cars are also larger. Larger cars are less fuel efficient. That's definitely part of the story. Another part of the story is that cars with a lot of acceleration tend to be less fuel efficient. And here, if you look at their acceleration versus their cost, you do see a positive association. And in fact, I think if you drew a line through this, it would be a line that went through like near a lot of dots. It sort of has a linear shape. What we're going to try to understand over the next few days is what does it mean to say some scatter plot has a linear shape? So we'll look at a lot of examples. But here's the first example that we've seen with hybrid cars that I think has a linear shape. All that means is that if you did draw a line through it, that line would be near a lot of the dots. Okay, but then the other issue is some of them are just huge. So one way to control for that is to look at the class. If you look at just the sport utility vehicles, then those tend to be the largest ones. And there's 39 of those hybrid sport utility vehicles. We could then just look at the acceleration versus price among those. And there, I still see a positive association, except that there are a couple that have terrible acceleration and yet are still really expensive. I'm sure those sold very well. Okay, but most of them seem to be kind of near a line that I would draw right around here, where among sport utility vehicles, the faster they accelerate, the more expensive they are. So that's one way to kind of get rid of this discussion of size, is to take a bunch of cars that are all, roughly the same size, at least they're in the same class. Okay, and among SUVs, what's the relationship between miles per gallon, fuel efficiency, and price? To me, this looks much more linear than the previous chart, which was all hybrids. Let's see if we can look at them both at the same time. Just the sport utility vehicles, like if you drew a line through this, it would go near a lot of the dots. Whereas this one has some other shape. It goes down and then over. Because probably all these over here that have really good fuel efficiency aren't sport utility vehicles. Sport utility vehicles max out at about 35. And here, that 35 is like here. So everything to the right of here is some other kind of vehicle, like a compact car. And so we've looked at some subset within here. And what we found is what I would call a negative linear association between fuel efficiency and price. So cars with great fuel efficiency tend to be cheaper. Cars with a high price tend to be less fuel efficient. Has something to do with acceleration. Okay. Now I feel like we have two things that we could potentially draw a line through. The SUVs, cost versus fuel efficiency, and then either the SUVs or all the cars, acceleration versus cost. When we've been talking about this, how much have we been looking at the units, the measurements on the axes? Very little. We've mostly been talking about the shape of the scatter plot, which if you measure this in miles per hour per second instead of kilometers per hour per second, wouldn't change at all. You'd still have all the same dots in all the same place. You just adjust the measurement on the x-axis. Or if you measured it in thousands of dollars instead of dollars, you just chop off 3 zeros from each of these, but you'd see the same chart. So when we're talking about linear association or association in general, it's something that tends to be independent of units. And so for that, we could use standard units. Standard units. Here's a function. Takes in any x, computes x minus the average of x, divides by the standard deviation of x, and now you have x in standard units. Is x a number? No, x is in a whole array. That's why you can take the average of it. So this is a function that takes a whole array of numbers, like all the different fuel efficiency values, and converts them from miles per gallon into standard units. We could then do that. So let's do that with the SUVs. Miles per gallon in standard units, cost in standard units, draw a scatter diagram, and we see exactly the same scatter diagram we had before. This one. Okay, so let me delete that one. Get them on the screen. Same dots, same configuration. Now we have standard units on the axis. Questions about what I just did? Wasn't too fancy. We just converted these. Okay, so is there a car that has average fuel efficiency and average cost? Yes, that one, right, is 0, 0. Everything to the left of this is below average fuel efficiency. Everything to the right is above average. Everything above this is above average cost. Everything below it is below average cost. And likewise, we could have the acceleration versus cost and build that version in standard units. So acceleration linearly associated in a positive direction with cost, and that is true if you express it in standard units as well. And everything's within plus or minus a few SDs of the average. So that's how data works. Okay. So I did all this just to show you some visualizations and talk about which were positive and negative associations, which are the general trend. As one goes up, one goes down, and which ones were linear and which ones were nonlinear. So even this was a negative association as the trend. It just wasn't a linear association. It had some other shape. But this was a positive association that was also linear, because if I drew a line, it would go near most of the dots. And as X got bigger, Y got bigger too. Positive. Okay. Any questions about what we're talking about when we're saying positive and negative, and what we're talking about when we're saying it's linear or nonlinear? Question? Yes, positive association means that for the larger X's, the Y's tend to be larger as well. So that means as you look at a cluster of individual points, let's find a positive association here, that have a high X value, they also have a high Y value. That's what a positive association means. And a negative association is the opposite. As you look at points with a high X value, they have a low Y value compared to the points that have a low X value. Another way to think about it is that in a negative association, you're going to see stuff in the bottom right corner. In a positive association, you're going to see stuff in the top right corner. And likewise, in a positive association, you'll see stuff in the lower left. In a negative association, you'll see stuff in the upper left. Thanks for asking. What is the point of converting to standard units? I guess my goal in converting to standard units was to show you that this notion of positive or negative association and this notion of linear versus nonlinear patterns weren't affected by the units that you chose. And so you could use standard units and still see the same trends. Converting to standard units is also a standard step in reaching the correlation coefficient, which is a measurement of linear association. I definitely hid these before. I've done them again. The correlation coefficient R is something that we can compute about any pair of numerical variables to describe the degree of linear association between one variable and another. That's what it's for. It's so commonly used that instead of saying correlation coefficient over and over again, which requires a lot of mouth movement, statisticians just call it R. And when R appears in a scientific paper, everybody knows what it means. It means the correlation coefficient. So let me show you how to compute it, and then we'll go through the equation. Any scatter diagram actually, I'll tell you about it first. Okay, so this measures linear association. It's based on standard units. So that's why we converted things into standard units, is that this notion of correlation is independent of the units in which you measure the data. And so if you switch things into standard units, then you can compute the correlation coefficient, which is a quantification of a linear association. R is always between -1 and 1. And here's what it means. When R is 1, then there's no noise in the scatter plot at all. It's a perfect straight line, meaning that every single data point in your data set has to fall exactly on the line with no deviation from the line. So if you can't draw a line that perfectly goes through all of the dots in your scatter plot, then you don't have an R of 1. You have an R of something else. Likewise, for R of -1, that means it's a perfectly straight line, but this time sloping downward. R of 0 means there's no linear association. And the technical term for this is that it's uncorrelated, since the correlation coefficient is 0. So what I've done is I've prepared a function that just makes up data. But it makes up data with a particular R. So if I set R to 1, it's just going to generate some random data. But notice that for R to be 1, it has to all exactly fall on this line. Any data set with an R of 1 is going to look like a line. It might have a different number of dots in the center versus the sides, but all the dots have to fall exactly on a line. If instead we choose -1, then it's a downward sloping line, a negative linear association. What's a data set look like that has R of 0? Well, here's just one example. We'll actually see other data sets that have an R of 0, but here's one example. Is if you have some X and some Y, two numerical variables, and for each individual, you plot them. Here's your X value, here's your Y value. And you get a picture that looks like a cloud where a high X doesn't tell you if Y is high or low, and a low X doesn't tell you if Y is high or low, then you have no linear association at all. What do you think is going to happen if I put in some other number here? It has to be between -1 and 1. But I could put in something like 0.9, which is very close to 1. And here's a data set with an R of 0.9. It's a bunch of stuff that falls pretty near a line. As I go to 0.8, it still looks like there's a line there. It's just almost like it's been obscured. There are now points that aren't near a line, here and here, but not very many of them. There are tons and tons of points that are very close to a line that I would draw. And if I did -0.8, I'd have the same degree of clustering about the line. It's just the line would be downward sloping instead of upward sloping this time. Yeah. Great question. So the question is, if you have an R of 1, is the slope always 1? Or what is the slope of this thing? So here we have a point at -2, -2, and a point at 2, 2. So the slope is exactly 1. When you express your data in standard units and your R is 1, the slope is always going to be exactly 1. Let's see what the slope starts to look like when we set this to 0.8. Here, if I were to draw a line through it, I feel like that line would hit, somewhere around here, right? That's actually not a slope of 1 anymore. That's some other slope, where even though I'm -2 in the X direction, I'm not quite -2 in the Y direction. And if I were to draw a line through here, actually, I feel like that line would end up, somewhere well above -2. After I did -2 in the X direction, I'm not all the way down here at -2 in the Y direction. That line seems too steep. There's like some other line that's a little bit more shallow. So the slope of the line that you might draw through is going to vary. And I'd say, if I had to draw a line through this, I don't know, you can't really do much better. I mean, you could draw any line and they'll all be equally bad, right? So yeah, it's only the case when R is exactly equal to 1 or -1 do you see a slope of 1. Okay. What else do you want me to try? Anything? I think I tried a half. What if I do like -0.3? What's that gonna look like? Think about it for a second. Oh, question first. Yeah, good question. So how could you have a data set where the R is 1? This is really a case where you're basically measured the same thing in two different ways. So if you had one column that was your height in centimeters and one column that was your height in inches, then you'd have the correlation between them be 1, because it's exactly the same information twice. But that's the only time you have perfect linear association, is when one just tells you the other, and all you have to do is just like adjust the units or something like that. What's the -0.3 going to look like? Downward sloping, lots of fuzz around the line, something like that. You might look at this and say, wow, there's actually like a lot of association here. Like if I look over here in the high side of X, all of them are on the low side of Y. And if I look over here in the low side of X, all of them are in the high side of Y. So yeah, an association, a correlation coefficient of -0.3 actually means that there's quite a bit of a trend. Sometimes people think like, oh, 0.3 sounds like not very much. But I'd say like, there's definitely information if you get a high value here that tells you that you're going to get a low value on the Y. Now for stuff in the middle, like, the X value is near the average. Well, the Y value is all over the place, somewhat up above and some below the average. So it doesn't really tell you a whole lot when you have kind of average X cases. But when you have a really high X or really low X, then it does tell you something about the Ys in this particular data set. When you get into the -2 or -0.1 range, now all of a sudden it's hard to see the line at all. Okay, so now we have some familiarity with the correlation coefficient. Let's talk about what it is. It's usually not something you use to generate data. Instead, it's something you use to describe data. So here's some data. Let's draw a scatter diagram so you can see what it is. It's just something I made up. And you can see, I took some points on a line, but then two of them I just moved. So there's still some kind of notion of an upward slope here, right? It's just sort of obscured by the fact that they're not all on the same line. These two got moved down. These were in, I don't know what units, because I just made up the numbers. But if we put them in standard units, what do we see? We see some values below average, and we see some values above average for X. Some values below average for Y, and some values above average for Y. If we draw the scatter diagram, we see the same picture, except now it's easy to see where the average is. It's right there. The next move might not seem obvious, but I'll try to describe why it is. The way you try to summarize the linear association for all these points together is to take the product of each point's position in standard units of X. So this one's at like 0.3, and its position in standard units of Y. So this one's at 0.8. So I got all the values in standard units. Here's the original units. Here's the standard units. Now for each point, I have only one number, which is what you get when you multiply X in standard units with Y in standard units. What R is, it's the average of this column, the average of the products of the standard units. So the R for this 6-point data set right here that we made up is 0.6. it's still a positive linear association. And this is some description of how closely these dots are clustered around a straight line if you drew a line that got close to all the dots. So that's the definition of R. You have to find y in standard units, x in standard units, take the product, and then average those. Average of the product of x in standard units and y in standard units is the correlation coefficient, which is a measurement of linear association. When you see a linear association and you want to measure it, this is a good way to do it. If you see some other kind of association and you want to measure it, this is a bad way to do it because this only measures linear association. Why the product? The most important feature of the fact that we're multiplying is that if you take something in the lower left corner, which means it's negative x and negative y in standard units, then you're going to get some positive product. If you take something in the upper right, which is positive x and positive y, you're going to get some positive product. And so if you have a data set with lots of points in the lower left corner and lots of points in the upper right corner, which gives you a positive linear association, then you're going to be averaging together a bunch of positive numbers. And the only way to get a negative product is to have either a positive y negative x, you're up here, or a negative y positive x, you're down here. And so you can get a negative linear association by having many more points up here and down here than you do here and here. But this product isn't just counting the points. It's also affected by kind of how far into the corner they are. So products get really big if something is really big in x and really big in y, then that's going to have a big contribution to the average product. Oh, interesting. So how is it that this equation, which I just told you about, never goes above 1 or below -1? This is a consequence of the fact that we're computing in standard units in the first place. And that means most of the values that we're dealing with are near the average, within a few SDs of the average. So it's kind of a mathematical result that you can't do this and end up with an R that's bigger than 1 or smaller than -1. Well, I'm not going to do a proof in this class, but a good place where you do this kind of mathematical justification of something that's true is in Statistics 88, or you'll do it in Statistics or Data 140 as well. Okay, so now you know what R is. We're going to talk about interpreting it next time. Thanks for hanging out.